Welcome you all. Today we are discussing on the deflection of straight beam, and this is under the strength of material curriculum of ME 403 classroom. And in this class we will discuss the different methods of assessing the deflection. So there are four methods of deflection of straight beam, and deflection, in fact the deflection is just not the deflection, it is the elastic deflection, because we will consider the straight beam to be elastic material. Whatever the deflection happens, if we remove the load or other transverse disturbance, the deflection will happen, or the deflection will be determined. Deflection will be determined by y. Y is the curve of the deflection curve, and x is the length along the straight beam. So the first method, where we are discussing on the double integration method, this is another name is the Macaulay's method. And this is the conventional, very useful method and very widely applied method. And this is the d square y dx square is equal to plus minus m by ei. M is the moment equation. So before doing the problem, first we have to have the moment equation. So the moment equation with respect to the x and the p. This equation involves the distance x from the support point and the load P, and this is a very standard equation. Y is the displacement curve, we call the elastic curve, and y is normally the deflection downward, vertical, and x is the horizontal. So there is an x and y relationship, and if you integrate it, you will find dy dx and y. So these are two equations we will get. In the first integration we will find the dy dx. Dy dx is nothing, the slope of the curve, deflection curve or the elastic curve, whatever we call it. And y is, first, when you do the first integration, there is a constant. The slope, the dy dx, the slope you can find plus a constant. The constant has to be eliminated with the help of the end conditions. There are end conditions are there, the support and end conditions are there. And if you further integrate it, there is another, you will find the deflection, and deflection will be, there is another integration constant. Now, if the beam is being loaded in between the two supports, the load is there. So the beam, basically this moment equation has two parts. First part is before the loading, second part is after the loading. More the loads, more the segregation of equations. So this is the major thing, that the constant of integration has to be eliminated. From one first part there is one integration, the second part is another integration, and the integration constants are to be eliminated with the end conditions. And there is a continuity of deflection, and that continuity equation, or the continuity of deflection equation, gives a point where the two parts are joined, or their adjacent parts are being, their deflection and slopes are equal at a point where the beam becomes continuous and the two adjoining parts are being evaluated. This is the main method. So we can find out this y, or the deflection curve, or the elastic curve from this equation. This is a very, very important method. We call the Macaulay's method. Now we move on the moment area method. Moment area method is nothing but we will find the same as the moment of the curve, and here the main thing is that this is a more graphical solution. This is more often an the first method is a mathematical solution. The second method, moment area, is a graphical solution. So we have to have a moment curve, length, and we have to have end curve, the bending moment curve, between the 2 points A and B. For in a shaft or in a beam, there are 2 points A and B. We have to find out the deflection at B with respect to E. Deflection of B with respect. So there is a relation between B and A. So whatever we find in the B with relation to E. First we have to find the slope. The first theorem says the theta or the slope between the two tangents, theta or dy dx. Theta is nothing but the dy dx. Since the deflection is very small, the slope is very nominal slope. So we can call it dy dx or tan theta become theta. So the theta between B and A is the area of the bending moment curve divided by EI. This is the first theorem of moment area curve. The tangent between B and A in the deflection curve or the elastic curve, the theta angle between the tangent between B and A, theta's angle between the tangent B and A is the area of the moment curve. So moment curve with EX between the 2 points, between A and B points divided by EI. This is the first. The second theorem says the deflection. Deflection is the moment of the area. Moment of the area, that is x into d theta, between B and A. Deflection is nothing but the moment of the area between B and A, that is the B with respect to A, tangent at A, is the moment of the area of the moment area curve divided by EI. So this is the method of finding out. So these two theorems are used for moment area method. And moment area is very important particularly for cantilever beam and uniformly simply supported. When the load is uniform, the central loading is there. So the deflection is at the midpoint. Maximum deflection at the midpoint of the simply supported beam. For such problems, the moment area method is very useful. The third method is strain energy method. Strain energy method, we sometimes call the Castich-Liano theorem. This strain energy method is very useful. We know the strain energy, this is one of the formula, is mx, the bending moment at a point x is square dx by 2 EI up to 0 to L. Suppose the length of the beam is L, any point x, we find out the equation of the bending moment, the square of it divided by 2 EI into dx, the small length dx. The energy, so moment, this is the integration of the small length of the beam. The energy stored there, now I integrated this. This is the strain energy due to bending. Mind that this U is nothing but the strain energy due to bending of the beam. There should be ideally as one strain energy due to the shearing of the beam. When the bending moment is acting, the shear force is acting, so shearing. But shearing, the impact of shearing is so small, so we eliminate that portion. So only we consider the bending moment, strain energy due to bending. And this strain energy is nothing but we have know that half P delta into U. So P is the load applied there. So if you know the P, you can find delta. If you find no, so this is the energy stored as per you know the strain energy due to bending is the P is the load applied on the. So we can find delta from this equation. This is very useful strain energy equation when the multiple loading is there. So when the loads instead of P there is P1, P2, P3, then we have to differentiate this. In fact, the delta is nothing but the differentiation of du dp. So that is a very useful method of finding the deflection of the beam. Now fourth is the superposition principle. Superposition principle is very important because the deflection, suppose a cantilever beam is being loaded at P1 and P2 here, we want to find the deflection at B. So in this case, so we first find out the deflection is B due to P1, that is Y1x. Now when you are finding out the deflection due to P2, we remove this, delete this P1. So separately we find out the deflection due to P1 when P2 is not there, deflection at B due to P1 when P2 is not there, which is dy y1x, and deflection at B due to P2 when P1 is not there, y2x. So if you do algebraically, you can find the deflection. So these are the four methods, and mind that the deflection is very important. The strength of material and deflection is very small. In fact, takes up all structures, beams, and this deflection is for elastic member. All the members follow the Hooke's law. So this is elastic member.